researchers discover numerous new exoplanets each year, raising the possibility that we might soon find an Earth-like world we could inhabit. Recently, scientists detected a signal from an exoplanet in the habitable zone, suggesting it might be of technological origin. But how would humanity travel to these distant exoplanets, trillions of miles away, and what technology would we need? Hello, and welcome to ZE. Please don't forget to subscribe and hit the bell icon. While it seems nearly impossible to journey such vast distances, scientists have recently discovered something in our solar system that might enable faster travel than previously thought. Before delving into that, let's explore how far some exoplanets are, the speed required to reach them, and the technology necessary for such journeys. The closest star system to Earth is Alpha Centauri, which includes Proxima Centauri. Proxima Centauri has two exoplanets, one of which, Proxima b, lies in the habitable zone. Alien hunters from the Breakthrough Listen project recently picked up a strange radio signal from this system. It occupies a very narrow band of the radio spectrum typically associated with human-made satellites and spacecraft, suggesting it could be a transmission from advanced extraterrestrial intelligence. Where is this mysterious signal coming from? And if we had to reach Proxima b to investigate, how would we get there? The biggest obstacle is the immense distance. Proxima Centauri is 4.2 light-years away from Earth. A light-year, the distance light travels in 1 year, is nearly 6 trillion miles. At the speed of light, 186,000 miles per second, it would take 4.2 years to reach. Currently, with no technology allowing humans to travel this fast, the fastest spacecraft is the Parker Solar Probe. In 2018, it reached a speed of 154,000 miles per hour, and at its closest approach to the Sun, it will travel at 430,000 miles per hour. Even at this speed, it would take 6,600 years to reach Proxima Centauri. But how fast can humans travel safely in space? The current speed record is held by the Apollo 10 astronauts, who reached a peak speed of 24,790 miles per hour. At that speed, it would take 113,000 years to reach Alpha Centauri. Chemical-powered rockets have taken humans to the Moon and powered long-range missions, like the Mars rovers and the Voyager probe, which is now in interstellar space. Speeds of 20,000 miles per hour seem fast, but not fast enough for distant exoplanets. The Space Shuttle, traveling at about 17,600 miles per hour, would take 165,000 years to reach Alpha Centauri. Current rockets need refueling, and there are no refueling stations in space. We need a new propulsion method. The direct fusion drive, a conceptual low-radioactivity nuclear fusion rocket engine, could produce thrust and electric power for interplanetary spacecraft. Developed at the Princeton Plasma Physics Laboratory, researchers hope to test it in space and eventually use it for missions within our solar system. This technology could send a probe to Titan in as little as 2 years compared to the 8 years planned for the Dragonfly probe. There is theoretically no practical limit to how fast humans can travel in space, apart from the speed of light. Constant speed in one direction isn't physically problematic for humans. However, accelerating to and decelerating from near light speed would pose challenges due to inertia, which resists changes in motion. Imagining travel at the speed of light, reaching the Sun would take just 8.3 minutes. But the universe is vast. Reaching the nearest large galaxy, Andromeda, would take 2.5 million light-years. Even with light speed travel, our destinations would be limited, necessitating faster-than-light travel. Warp drive technology, popular in science fiction, involves manipulating space-time to move faster than light. Theoretical constructs like the Alcubierre warp drive propose bending space-time to enable such travel. As a ship travels, space ahead contracts while space behind expands, creating a warp bubble of flat space. Some physicists believe this could be possible in the future. Wormholes, predicted by Einstein's theory of general relativity, could also provide shortcuts through space-time. Though never observed, they theoretically connect distant points in space. Creating a stable wormhole would require exotic matter with negative energy or mass, which is currently unknown to exist. The energy required to maintain a wormhole would be immense, beyond current technological capabilities. Humanity's quest to travel faster in space has always been driven by our innate desire to explore the unknown. From the early days of rocketry to the latest advancements in space technology, the pursuit of speed remains a central theme. Understanding the current limitations and future possibilities of space travel speed involves a deep dive into the realms of physics, engineering, and imaginative theoretical concepts. Current achievements in space travel. As of now, the fastest human-made object is the Parker Solar Probe, which was launched by NASA in 2018. It is expected to reach speeds of up to 430,000 miles per hour, 700,000 kilometers per hour, as it approaches the Sun. This speed, while impressive, is still a fraction of the speed of light, which is approximately 186,282 miles per second, 299,792 kilometers per second. Human spaceflight, however, has been considerably slower. The Apollo 10 mission, which holds the record for the highest speed attained by a crewed vehicle, reached a top speed of 24,791 miles per hour, 39,897 kilometers per hour, during its return from the Moon. Achieving higher speeds for manned missions involves overcoming significant engineering and safety challenges. Physics and limitations. The primary limiting factor in increasing space travel speed is the fundamental laws of physics, particularly Einstein's theory of relativity. According to the theory, as an object approaches the speed of light, its mass effectively becomes infinite, requiring an infinite amount of energy to propel it further. This makes reaching or exceeding the speed of light with current technology an unattainable goal. Another significant factor is the propulsion technology used in space travel. Chemical rockets, which have been the workhorse of space exploration since the mid-20th century, have inherent limitations in terms of fuel efficiency and energy output. These rockets can only carry a finite amount of fuel, and the amount of thrust they can generate is limited by the chemical properties of the propellants. Innovative propulsion technologies. To surpass the limitations of chemical rockets, scientists are exploring various advanced propulsion systems. One of the most promising is ion propulsion, which uses electric fields to accelerate ions and produce thrust. Ion thrusters are much more efficient than chemical rockets and can achieve higher speeds over time. NASA's Dawn spacecraft, which used ion propulsion, was able to change its velocity by over 25,000 miles per hour, 40,000 kilometers per hour, during its mission. Another futuristic concept is the use of nuclear propulsion. Nuclear thermal rockets, which use a nuclear reactor to heat a propellant like hydrogen, could potentially offer much higher efficiencies than chemical rockets. Additionally, nuclear fusion, the same process that powers the Sun, holds the promise of providing massive amounts of energy for propulsion, although practical fusion reactors are still in the experimental stage. Theoretical concepts and future possibilities. Looking further into the future, theoretical physics offers some intriguing possibilities for faster-than-light travel. One such concept is the idea of wormholes, which are hypothetical passages through space-time that could create shortcuts for long journeys across the universe. Wormholes are predicted by the equations of general relativity, but their existence and practicality for space travel remain purely speculative. Another theoretical proposal is the Alcubierre warp drive, which involves bending space-time itself to achieve faster-than-light travel. The concept, proposed by physicist Miguel Alcubierre in 1994, suggests that a spacecraft could compress space in front of it and expand space behind it, effectively allowing it to travel faster than light without violating relativity. However, this idea requires exotic matter with negative energy density, which has not been proven to exist. Conclusion. While the speed of space travel has significantly increased since the dawn of the space age, we are still far from achieving the speeds necessary for interstellar travel. Current technology is bound by the laws of physics and the limitations of existing propulsion systems. However, continuous advancements in ion propulsion, nuclear technology, and theoretical physics hold the potential to revolutionize space travel. The pursuit of faster space travel is more than just a scientific endeavor. It is a testament to human curiosity and our desire to explore the cosmos. As we continue to push the boundaries of what is possible, we inch closer to a future where the vast distances of space may one day be traversed with ease, opening up new horizons for exploration and discovery. A recent discovery in our solar system might allow faster travel. Researchers from the University of California, San Diego, found a new gravitational superhighway system by studying the orbits of celestial bodies. These space manifolds, or gravity channels, enable faster movement through space. This discovery could enable spacecraft to reach outer planets more quickly, opening new opportunities for interplanetary travel. Combining this with future spacecraft technology, humans may soon explore the universe more extensively.